All right, so if we were to draw free body diagrams for those two coins, you've got the 20-gram coin, you've got the 50-gram coin. This is going to experience an FG of somewhere around 0.20 newtons, but this is going to have a bigger force. This is going to have an FG somewhere in the ballpark of 0.50 newtons. It's got more force. Why are we getting the same acceleration? I need you to run that by your neighbor real quick. How can that be? This object's got more than double the FU. How is this shaking out? It's got more force. Why isn't it hitting the ground quicker? It didn't, right? They hit the ground at the same time, but I'm saying this one's more than double the force of the other one. Why is that shaking out? Who was sitting by somebody smart there? Nobody was sitting by somebody smart there? So let's throw that onto the pair deck. Okay. What's up with that? The 50-gram object is experiencing a greater gravitational force. Why does the 20-gram object hit the ground at the same time? Be mindful of how you get from grams into kilograms. Keep in mind there are 1,000 grams in 1 kilogram. All right, so gravitational acceleration of the two objects is equal. Okay, but we want to talk about why that is, okay? The ratio between the FU and the mass are the same for both. Okay, and a couple people threw that out here in the math. So you've got 0.20 newtons and 0.020 kilograms of mass. That's going to be the same as the ratio of 0.5 newtons to 0.050 kilograms. Okay, and if you shake that out as an equation, you're going to get the same acceleration for both of those. So the FU equals the FG. That means that MA equals M times 10 newtons per kilogram. Wow, that doesn't like my hand touching the screen. And so the M's are going to cancel out, and the acceleration is equal to 10 newtons per kilogram, but we don't tend to talk about acceleration in those units. That's equivalent to 10 meters per second squared. And again, masses cancel out. It's independent of the mass that I put in there. I'm going to get an acceleration of 10 meters per second squared. Okay. We talked about this in the comments after the video analysis lab, that horizontally You see a linear position versus time graph and a horizontal velocity versus time graph. Those are hallmarks of the constant velocity particle model. And then vertically, you've got a parabolic position versus time graph and a linear vertical velocity versus time graph. Those are hallmarks of the constant acceleration particle model. And as far as explaining why that's happening, the why comes from the theoretical models. Horizontally, there are no unbalanced forces, but vertically, there sure as heck is. And as a couple people mentioned on the pair deck, if you have a situation where your unbalanced force is equal to your gravitational force, you have free fall, you have an acceleration of 10 meters per second squared. Okay? All right. So glad to have that fresh in everybody's mind. What we're going to do with that today then is characterize this projectile launcher, which is to say try to figure out some information about it. So let me show you what it does here, if I can get this to chill out. I've got a little angle measuring thing here on the side, okay? This little app over here measures the angle. What I'm trying to do is get it to launch perfectly horizontally. So it's kind of like the coins when they're coming off the table, they come off flat. I'm trying to launch the ball out of this thing flat as well. And I've got a low speed setting. That looks like this. I might need the assist. Just saying, Quacky. Ooh, hey, speaking of the ball flying around the room here, I go the wrong direction with this. Come on, buddy. Hey. Always. Got to use the right hand roll here. That was my problem. There we go. Before we learn this lesson the hard way, this ball is really nasty to cell phone screens. So you might face your phone down if it's out on a table. Because if somebody makes an errant throw, which, let's be honest, this is AP physics, okay? The athletic quality in here, maybe not what it would be in other classes. Your phone screen will die an untimely death. All right, so low speed setting again looks like this. Sports. Medium speed setting looks like this. And the high speed setting looks like that. So what I would like you to think about over on the pair deck is what do the Vx VT graphs look like? What do the Vy VT graphs look like for that type of motion? And use different colors for the different launches there. We got low, medium, and high. Right now, I'm just asking you to think about the velocity versus time graphs. Something that might help you with the velocity graphs is to go ahead and think about, or maybe even sketch in your notebook, what the position versus time graphs look like. All right, let me throw this up here for you. So this is what it looks like inside the Pear Deck right now. Kind of a fair bit of variation. So can you take a moment and chat with your neighbor about what you got or why you got it?
Yeah, except the thing is, position versus and if you can
Yeah, so like high, weak, tall.
So then would
and then
the more
wide.
And then
wait, no, the one that
so
goes
it's changed.
Yeah, down.
Yeah, so like
Yeah, because it's not.
Velocity starts at 0 for 1.
And we know it's looked back.
no, it should because it comes out as
Straight. Yeah, but that's on the axis. On the y-axis, it's only
oh, I'm not so
not that.
well
It's going down.
yeah.
So it should start at 0 for all. And go down at the same rate, too.
All right, I'm going to lock this out for a second because I just want to chill. I just want to share some of the examples that I'm seeing. So there are a few examples up there on the screen, and I got that frozen. Okay, cool. Now it's unlocked. You can do what you need to do. So, there's a fair bit of variation. Maybe not so much in the upper graph. You've got one difference over here. Otherwise, they're kind of drawn it like that. Vertical velocity graph. I think what might be helpful for you is if you were to have the position versus time graphs referred to as well. So could you be a dear and send somebody from your group up to grab a whiteboard and lay out all four graphs? Think about the XVT, think about the YVT, the VXVT, the VYVT. And then I'll give you a little extra information with this too. I made some measurements a little bit ago on this launcher. I should say the height from the bottom of the ball to the floor. When I measure that distance, okay, so when it comes, and we should be aware of this as well, the ball's only interesting from the instant it leaves the launcher till just before it hits the floor. But when I measure up from the floor to the bottom of the ball, that's 1.17 meters. So think about how that 1.17 meters would show up in these graphs here as well.
Position.
These are
I think what you're trying to show is that because it's a fixed
we
distance
don't know how
from
far
the
to
launcher
go.
to the
So we
solar.
go far.
What's up?
So it's like,
Should we do all three of the speeds?
I think the ground should be.
That's fine. Okay.
No, I gotta
Just one. Just one. And then this one like starts there.
Oh, yeah.
It starts at 1.7. This is the one.
Wait, so then.
Yeah.
No, because that's
What do you consider
so
the-
it continues
Oh, yeah.
constantly from 0. So that
That's,
it doesn't do enough, I don't, because just launching it as horizontal as possible. So it looks like
oh, yeah.
so then
Equals
that
one.
was 0. So
Start saying a high position.
okay,
It was that.
no, this is that's 1.7.
Oh,
Because we don't know how far to go that way.
Okay, wait.
Yes, that makes sense.
I just like.
Because this one
It's hard to choose for all three speeds.
all three speeds, yes.
Okay. Let's have one speed and the other be another speed, and then we'll just draw it in the first color. You see what I'm saying? So then we can tell which is which. So which one do we want? They all start from here. So like let's.
Fastest one.
If you
The
consider.
black one? Okay. So then you need to draw the
Oh.
black one on the screen. This one is just a higher line.
No, we know you're right.
And this one.
Position specified.
Yeah.
Right.
No. Because it's this. It's no. So it's not this. This changes, right? Because it goes this way for longer. Yes. But this black one like moves that way. Because it starts moving from 0 to farther distance,
Yeah, but then.
which is a farther time.
If
yeah.
we could go like this. That's
Yeah.
like
That's
Yeah, but you starting
Yeah. Well, I mean, it's a little more like
Yeah.
that.
No, but you're starting from 0, because then you're starting like 1.
Yeah. Okay. I'm just kind of sketched over here. I don't know how to see something. What I'm saying is like it's closer to horizontal. We're going down at that. So like this part is a problem, and that part is constant. Do you see what I'm saying? Or am I making literally no sense?
Yes, I think
So I told you 1.17 meters, right? Where is
Let's take notes because. So. How would you suggest we do that thing? Because it's a different slope if we do that. Because then.
So,
Yeah.
yeah.
Are there any other numbers
higher
besides that too? That show up like-
Yes, that is correct. Okay.
Yeah, I wrote it wrong.
Trying to make the graphs as quantitative as possible. I'm telling you up front, 1.17 meters. Is there
I'm gonna
anything
make
else?
dashy blue the low speed and solid blue
Oh, wait.
medium speed and black side. So like.
The slowest one, because it's like.
And then here, dashy blue. Dashy blue is the lowest, lowest speed, so this guy's gonna move down.
The way to this.
Yeah.
Then.
Now it's dashy blue.
Yeah, that's fine. Okay.
you wanna have your? Oh, shit, so.
Oh, yeah.
So these would just be, is that different starting graphs? Wow, I'm big dumb. Okay. Alright.
Okay, so change your position.
So just, they take,
Oh, that's in Y position.
Right?
yeah, so, yeah.
Yeah, it should be the same.
They all have to start.
Oh, yeah, you're right.
But they take longer, like, as the speed, they take longer to reach the ground.
Yep.
So that's, yeah, that's good.
It means square.
Wait, do you have to put in numbers?
I mean, just the one part, if you didn't give us
Anything?
anything else. Well,
We know these.
yeah, we know these slopes.
This one should be the one.
Okay, so the,
Counting just like four zones. And then this one.
So that's.
right? Figure anything else out, because we can't figure these out if we don't know how far the travel's
Yeah,
in
I
here.
mean, you don't know the time.
Yeah, so we need to backtrack and figure it out. Yeah.
Figure out anything else that you know that.
We got 3 numbers.
Cool.
So this one must be.
Make a mess. So what if that graph is 10? What if that graph is 1.17? Okay. So yeah, relate those things. Hey, you're not all picking up on what I was putting down by having us do that coin thing first, okay? These are all launched flat out of here. Obviously, the high-speed setting lands a little farther away. Regardless of that, what things should be the same for all 3 settings, okay? So be mindful of that when you're looking at your graph.
Yeah, it goes in.
The wide.
And do go back over into the Pear Deck and revise your graphs if you haven't yet.
Normally have different. Yeah, but they have. Yeah, I think you're right. Yes, so this is supposed to be just one,
Yeah, this one's all.
one or one.
Alright, I'll put this one. And this guy, I'm gonna need your black.
Wait, but if it's all going at 0.44 seconds,
That's how far it goes though.
then all of these would have to be up.
No, because they have different exponents. So they all the same amount of time. Of course. It's the same amount of time. Yeah. So if they are different velocities in the same amount of time,
No,
the fastest one, of course, would go the
the better.
furthest, right? So we should be.
They're moving up.
Oh, wait.
And they should all be.
It should be,
Oh, yeah, that's gonna be down.
We aren't thinking about it at all on that one.
Okay.
They make it, yeah, it shows just one. Yeah.
And then the area on this one is that number.
Right.
Yeah, because it don't really matter what.
Mr. Hardy, are we
Yo.
assuming we're just graphing the first time it Instagram?
It's only interesting until just before it hits the ground the first time, yeah. So from when it leaves the launch until hitting the ground. So graphs wise, so here are a couple of things that I'm seeing in the Pear Deck. I need you to compare and contrast these two and think about the things we were discussing earlier and which of these is more consistent with our current understanding of projectile motion. Okay. So what advice would you have for that other person? Ponder that with your neighbor quickly.
It's affecting one else in the
There will be in a second, so you got about a half a second. Okay.
Yeah, the first one says.
Yeah.
I don't think it's.
Well, this is
That was
travel.
like before.
That makes sense.
But now you know.
Yep.
All right, I'm gonna put you in charge of this.
It's just really, I haven't seen.
Yeah.
This one covers, like, this one is solid.
All right, and then I'm going to give you some additional information here. Emily's going to try to eyeball where this thing's hitting. So on the low speed setting, it's going to be kind of close in here. So, all right, so if you want to kind of check where you think it's going to hit at.
Me?
Yeah.
Safe.
So did you see it?
Yeah.
Okay, so just kind of just drop the ring on there. It'll be like a target type thing. We're thinking right around there-ish. Sports! All right. What do you think? Whoa. Kobe, you're like a D1 athlete. Go over here and catch stuff. All right. Sports. What do you think, Em? Was that about spot on?
Yeah, pretty much.
So where would you say it's hitting?
Right about 4.45.
Let's check that again. So it kind of hit the back end of that
So more closer to 40.
to 50. Or I'm sorry, like the back end to me is that side of it, right? But
That's what it is.
let's watch. Yeah. Go more towards William from me. Yeah. All right, let's check it out. All right, here we go. Yeah, right?
50.
Bullseye. Okay, so that's 1.50 meters. So on the low speed setting, boop, 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 boop. All right. And then let's check it out on the medium setting. Pretty spot on-ish, just off to the side. So what is that at ish?
About
How many meters do you think? 2.40?
Yeah.
Alrighty. So, I'm sorry, I've got this frozen. All right, so medium setting goes a little farther. And if we go high speed setting, let's get the bullseye. I think it's going a little past that, isn't it? kind of
I just think it's getting more.
shift it more that way. Yeah, more left. All right, Alex, you want to watch this too? See what you think. Let's see, land past that or oh, this thing is just going, man.
Just go to the side.
1 second, sorry. Oh, all right. Just past it, right?
Yeah.
So that's 3,
Point two.
3.2. All right, cool.
Goes
Somewhere. Thanks, boss. All right. So low is 1.5, medium is 2.4, high is 3.2. Think about where those numbers will show up on your graphs, and can you figure out as much as possible quantitatively? What numbers are going to show up this year?
We have this.
So we have distance travel.
So
Five.
So time goes.
well, we can figure out. So what's the change?
Like in so it's like that's
Negative, right? So negative. That's the change in condition. How does the change in condition show up? Zero. Yeah. So live with that.
Okay, so now we can take the.
Oh.
Yeah,
We don't know the time, so
we can decide.
the area of it. So the area is.
Vertically. They all go 1.17 meters.
We don't want the vertical.
Addition.
Also,
Area.
Yeah, this is the area.
Yeah.
We can't find it. I'm just saying we can show them the area.
so like, I'm looking for like.
Bro. So it's 17 times 9. It's 17 times 9. So make that negative 10. To make the math next.
Well, actually. That is not it.
So it starts out at exactly. Look at speaking zero, so it's change in position.
So 5
1
divided by area.
Oh.
So you have
417.5, and that's the square root of that.
you got the area. What is the slope?
Oh, here's that.
We're talking about area, that's the acceleration. So you know the area, you know that slope.
I know.
Yeah. What's
And that's the same for all.
Oh, you know, it's.
That. Alright, so then we'll do that divided by that,
There you go.
and then do that for each.
That is. All right, last slide on the pear duct then is and I gotta fix this here. Gosh darn. No. Last question on the Pear Deck is to list out your velocities. How fast is it going on each of those settings?
So we can get they all look at ground.
1.5 is already.
They always have to be started.
Wait, it's 1.5 based on. You don't. So the area is equal to 1.5. So area is equal to 1.5 based on site. Oh, so now we have.
All right, youngsters, go ahead and store those boards in the back.
I'll put the board in the back.
Yeah, if you get here, put your arms in the sock back, that's greatly appreciated.
They're always like way harder than that.